Hello and welcome to another episode of Math with Sohn. Today we're going to be doing things to remember for momentum, and this is going to be geared towards the AP exam, but it's also with any other class as well. So the only thing you're provided with on the AP exam is these two formulas right here, and momentum is way more than two formulas. So you're provided that momentum is a vector. That little hat on the top indicates it's a vector, which is equal to mv. You're also provided the change in momentum is equal to force times time. And then what you can use from that is finding the area under the curve. You would have to recognize anytime you're multiplying two things, it would be, if you're provided those two things, the area underneath that curve. Okay? Now this is the force from like an outside force. It has to be an outside force. If you had a ball that is just sitting here doing its own thing, its current momentum would equal 0. But then if it's struck by anything, if it is struck by a force, and that force was, 4 newtons times 2 seconds, then it would have a momentum of 8 when it's finished, because it would be changing from 0 to 8. All right? Now that is oftentimes confused with if you have two rocks going towards each other, they will experience a force. That force will be equal and opposite according to Newton's third law. Because the force is equal and opposite, their combined change in momentum is going to equal 0, because if we look at the system with both of them, there is no change in momentum. But if you look at any one individual rock or ball, there would be a change in momentum. So here we looked at it as an individual thing, assuming this force we did not know and think about what was happening to this ball on the left side. If we were only thinking about the ball on the right side, that one had a change in momentum, but the combined would not. Okay? So the other thing that you have to memorize with momentum, and this is a big one, is the formula. You got m1v1 plus m2v2, and these are initials, must equal m1v final 1 plus m2v final for 2. This is for elastic and bouncing. So if it glances off or bounces off, if it doesn't stick, that's the formula. The definition for elastic energy would be slightly different. If it is considered elastic, not only will it use this formula, but if it is considered any perfectly elastic, but you don't have to say the word perfectly elastic, if they just say elastic, that means that kinetic energy is conserved. And if kinetic energy is conserved, then you also have 1/2 m1v1 squared plus 1/2 m2v2 initials squared must equal 1/2 m1v final squared plus 1/2 m2v final squared for that. Okay, so if it is elastic, then this would also be true. Now, normally this gets intimidating because you got like 4 different things here, but typically one of them 0 in the beginning, so it's actually not as bad as you may think. That is only if it's elastic. It doesn't have to be conserved with kinetic energy if it's just bouncing, and it would still use this momentum. Another thing to memorize while we're here, no matter what, momentum is always conserved. Conserved. Even if it is not elastic, even if it's not bouncing, which brings back us to the next thing, where we have a inelastic collision. Specifically, it has to be stuck together. Okay, so if it's inelastic, they have to be stuck together. Then we still start it with m1v1 plus m2v1 or initial must equal, they're stuck together. So they would be stuck and glued together as one mass and have a singular v final here. If they are stuck, they can never be inelastic. they can never have kinetic energy conserved here. Okay? You are going to lose some in that splat process in the form of friction. Okay? So no energy would be conserved for inelastic collisions. All right. Here's the thing that I think that we need more practice with, and that would be the transferring of energy. Okay. So there is always going to be more transference in elastic, which is more like appropriate to say bouncing collisions. And we're going to prove it. And there will be less with stuck together collisions. So what that means is if you have a rock going this way and we have a ball that's going the opposite direction, when they bounce, if they bounce off and start going in opposite directions, this ball right here will take in more energy than if it were to have the ball go here and then this one maybe going this way, than if they got stuck together and were leaving together. All right? Now, you typically see this in a pendulum problem where you have something here and they tell you, hey, a ball is thrown against it. How high will it shoot up? Or versus a ball that is stuck to it, how high will it go up versus if it were bounced or if it went through. If it goes through, that's going to be the worst. All right? So let's show you mathematically why that is the case. All right, so still with transference. All right, we got m1v1 plus m2v2. If it is in a bouncing equation, it would be m1v final plus m2v final for 2. Versus if it is sticking, again, it would be m1v1 plus m2v2 would equal m1 plus m2 v final. All right? So with it sticking, that would be over here, the v final would equal m1 v1 plus m2 v2 divided by the combined mass, which doesn't cancel out because they're stuck together, would equal v final. Now we are dividing by more things here. We are dividing by an m1 and an m2. All right? Versus over here, even if you think of them going in opposite directions, so let's say that this one is going to the right and this one's going to the left, that would make this a minus. And then afterwards, this would be going to the left and that would be going to the right. So going back to our diagram, one was moving to the right and then it was moving to the left, and then one was moving to the left and then it was moving to the right. So that's what the negatives would be doing. And that would make this one negative as an end result, which is also important because that actually makes this even more pronounced as a bigger V final in a transference with it bouncing off. All right, so let's solve for the V final for let's solve for V final 2 because it wouldn't matter. We'll talk about the second ball here. That means that we would have M1 V1 minus M2 V2. We would add over the M1 V final would equal M2 V2 final. Then you would divide. And if we divide by the mass of 2, there's two things here that would let us know that the V final for this situation is bigger. A, we're dividing by less mass. B, you have an adding of two things and a subtracting of one, and that makes it even more. And you could also think of this one as this may have originally been moving to the left, so this one could also be a minus. All right? So we are dividing by something smaller, and you are combining potentially more things on the top. It's a double whammy. It is going to have a bigger final speed, which also proves that at least more kinetic energy is conserved. All right? So more kinetic energy is conserved. If it's perfectly elastic, all the kinetic energy will be conserved. Last but not least, center of mass. The velocity of center of mass never changes unless there is an outside force. Okay? So that would mean that if you have this ball doing this thing, and you have this ball, maybe it's going even faster, but it might be smaller. The center of mass will be somewhere in here. That velocity of the center of mass will continue to be the velocity of the center of mass and the velocity of the center of mass and the velocity of center of mass. It won't matter if they never hit each other, if they hit each other, if it's elastic, or it's inelastic. As long as there is no outside force, then the velocity of the center of mass, which they often call COM, will remain constant, okay? Now, if you decide to, all of a sudden throw some other ball into the mix and hit these two balls that were doing their thing, then it would change. But unless there is some sort of outside force, there will be no change in the velocity of the center of mass, regardless of the situation, okay? That's going to do it for this one. Until next time, everybody, stay positive, and I will see y'all later. Bye.